Hello champions, welcome to Gagan Online Academy Kadapa. Today we are going to start NEET Physics, Units and Dimensions. Physics is not tough, physics becomes tough only when basics are weak. Units and dimensions are not chapters, they are foundations. If the foundation is strong, formulas work for you. If the foundation is weak, formulas work against you. This is NEET, no guessing, only clarity. Measurable quantities are physical quantities. Anything which is measured, that is called physical quantities. If I say length, mass, time, force, energy, these are physical quantities. Reason is they can be measured. Length can be measured in meters, mass, right, in kg, time measured in seconds, like that. Force, newtons, energy is measured in joules. So these are measurable quantities. So all measurable quantities are called physical quantities. It's not measured. So this is not a physical quantity. Knowledge also not measured, right? So this is not a physical quantity. Fundamental quantities. There are 7 fundamental quantities. They are fundamental in physics, means basic physical quantities. They are length, mass, time, temperature, current, amount of substance, luminous intensity. These are fundamental physical quantities. Length, it is measured in meter. Mass, it is measured in kilogram. Time, measured in second. Temperature, SI unit is Kelvin. These are units. We must remember their SI unit. Current is measured in amperes. Amount of substance, mole. Luminous intensity, candela. These are the SI units. These 7 are called fundamental quantities. Other quantities derive from this. So that's why these are called fundamental quantities. Everything comes from these 7 fundamental quantities. Have a look at the screen. 7 physical quantities are there. Everything else comes from them. Length, meter, mass, kilogram, time, seconds, electric current, ampere, temperature is measured in Kelvin, amount of substance, mole, right? Symbol is MOL. Luminous intensity, symbol is CD, it is measured in candela. You must remember these 7 fundamental quantities. Derived quantities. These quantities depend on fundamental quantities. By combining length and time, we get velocity. Velocity is born. See here, length by time. Length, simply distance, right? Distance by time is velocity. We must say displacement by time, right? Okay. Again, by dividing velocity by time, we get acceleration. By multiplying this acceleration with mass, force is created. See, length, time, velocity, acceleration. These are created by length and time. See here, length by time, velocity by time, acceleration into mass, force. So by combining this length and time, velocity is known. From velocity and time, acceleration appears. From acceleration and mass, force is created. This force, acceleration, velocity are derived quantities. These are derived from length and time. Next is dimensions. Dimensions tells us how a quantity is made or how a quantity depends on. We use length, mass, time. For length, we use this letter capital L. Next, for mass, we use M. For time, we use the letter T. L, M, T. Most of the physical quantities are expressed in L, M, T. Above L, we write A. Above M, we have B. And above T, we have C. So, this is identity card. This is dimension is called identity card of physical quantities. So dimensional is identity card. Identity card of physical quantity. So we express physical quantities using these dimensions length, mass, time L, M, T, and they are raised by powers A, B, C like that. We must know how to write dimensional formula. See, let us write some dimensional formula. First one, velocity. To write dimensional formula, first we should know mathematical expression for each physical quantity. Velocity is defined as displacement by time. Mathematical expression is displacement by time. Displacement is nothing but length. So I am writing length, that is denoted by L, by time T. Now L, this T power 1 goes numerator, it becomes T power minus 1. From velocity, I am writing acceleration. Velocity by time, that means change in velocity by time. Change in velocity by time. That is acceleration. So velocity, what is the velocity dimensional formula? L T power minus 1. So I am writing L T power minus 1. For time, here I am writing T. So L, here also T power 1, L T minus 1. This plus 1 also becomes minus 1. Minus 1 and minus 1 becomes minus 2. L T power minus 2 is the dimensional formula for acceleration. Next, force. We know force is equal to product of mass and acceleration. So mass into acceleration. Mass into acceleration. Dimensional formula for mass is m. Okay. Then acceleration. Just we derive dimensional formula for acceleration is L T power minus 2. We write here L T power minus 2. So finally m L T power minus 2 is the dimensional formula for force. We know force into displacement. Force into displacement. Product of force and displacement will give us this work. Displacement. Force dimensional formula is m L T power minus 2 into displacement is nothing but L. So m L into L square T power minus 2. For work and energy also, we have same dimensional formula. So remember this velocity, acceleration, force, work, energy, dimensional formula. After that, let us discuss for pressure. Now let us write dimensional formula for power. We know power, right? Work by time or rate of work. Rate of work is defined as power. So we know formula, dimensional formula for work, that is m L square T power minus 2. Time is denoted by T. So from this we get m L square T power minus 2. This T power 1, right? We write T power minus 1 if you write in numerator. From this m L square T power minus 2 and minus 1. By adding we get minus 3. So this is the dimensional formula for power. Next, pressure. Force per unit area. Force per unit area. That is the basic definition. So force we write M L T power minus 2. This is dimensional formula for force. By area means length into breadth. That is L into L. That is L square. So M, here one L gets cancelled. This 1L is left in denominator. So L power minus 1, T power minus 2. This is for pressure. Next, mass by volume. Mass by volume. If we divide mass by volume, we get density. So mass is, dimensional formula of mass is M. Volume, length into breadth into height. That means 3 dimensions. L into L into L, that is L cube. You write M, L cube. L to the power of this plus 3 becomes minus 3. Right? Next, T power 0. T is missing. If any dimension is missing, you can put 0 above that a letter. Uses of dimensional analysis. By using this dimensional analysis, we can say whether an equation is right or wrong. That means correctness of a formula or equation can be checked. So to check whether an equation is correct or wrong, okay? For instance, S is equal to ut plus half at square. Right? We know this formula. Now I want to find whether it is right or wrong. Correct equation or wrong equation. S is displacement. So for this, for displacement means length, dimension is L. Again, for velocity, here U is initial velocity. Velocity is, dimensional formula for velocity is L by T. Here time, dimensional formula T plus half. Acceleration, L T power minus 2. Dimensional formula for acceleration. Again, next to T square. Okay. Now see here, left side of the equal symbol we have L. By cancellation the T and T we get L. Half T power minus 2, T power plus 2 gets cancelled. L we got. Each term is having, see this is first term, this is first term, second term, third term, right? All terms are having same dimensional formula. Here L dimension, here also L dimension, here L dimension. So from this we can say this sentence, this equation is correct. Don't think of this numerals, numbers, right? Coefficients. In each term must have a same dimensional formula, dimensional letter. You can find a relation between physical quantities in a formula. Suppose we know time period of a simple pendulum T is equal to square root of L by G. So this kind of relations can be created using dimensional analysis. One more use is we can convert units from one system of units to another system of units, like kilometer to meters, right? Grams to kilogram, meter per second to kilometer per hour. So in this manner we can convert units from one system to another system. These are the uses of dimensional analysis. Have a look at the screen. See here, checking uses of dimensional analysis. You can check an equation whether it is right or wrong. I told you one example also, S is equal to ut plus half at square. And you find relation among physical quantities. Suppose T is equal to square root of L by G. This is time period for a simple pendulum that depends on length of the pendulum and acceleration due to gravity. Next, you can convert one system of units to another system of units from kilometer hour to meter per second, centimeter to meter, grams into kilometers. So that can be done using dimensional analysis. Limitation of dimensional analysis. See here, we dimensions analysis cannot find numerical constants like half, 2 pi. These are constants. We can't find numerical constants using dimensions. And they won't work for trigonometric ratios, sin theta, cos theta, tan theta. And finally, they cannot say the direction of vectors. Okay, these are the limitations of dimensional analysis.